Okay, so this is our first problem, and how to change yeah, yeah. So this is our first problem, and we'll be doing the solution. Last week, this was done that Hilbert basis theorem and free modules. So, yeah. Now we'll start doing the solution for this problem, that is, let M be an A module and let N1 N2 be the submodules of M if M by N1 and M by N2 are Noetherian. Then so is M by N1 and intersection N2. So under the conditions of the problem, we have the exact sequence 0 by n1, m by n1 intersection n2, and m by n2. Here this inclusion map and this is pi map. So we know that in an exact sequence, if first and last terms are Noetherian module, respectively Artinian, then the middle term is also the same. So m by SNET2 is Noetherian, respectively Artinian. Respectively Artinian. Now so this is done. We can go to the next problem, that is so okay. We'll be doing interesting consequences of some problems. I will introduce some of the uh, definitions, and then we'll be proving an important result, that is theorem. if A is Noetherian ring, then spec of A is Noetherian topological space. I think this is important. Also, is the converse true? Now, this is very important theorem in algebraic geometry. So first we will introduce, that is, definition of a Noetherian topological space. So a topological space X is said to be Noetherian if the open subsets of X satisfy the ascending chain condition. That is, the increasing chain of open subsets is stabilized always, that is finite, or equivalently the maximal condition. So since, okay, observation, since closed subsets are complements of open subsets, it comes to the same thing to say that the closed subsets of X satisfy the descending chain condition, or equivalently the minimal condition. Now, we can do a topological problem. we need very much of topology on uh, so I have introduced uh, mm, that is irreducible closed subsets. So first let do a lemma, that is uh, a Noetherian space is a finite union of irreducible closed subsets. Now for this okay, so yeah, I think should prove this. Now okay, recall. Uh, a irreducible closed subset A implies a union A where if this happens, where A1 and A2 are closed in A, then one of them is trivial. That is, it cannot be written as the union of two proper closed subsets. So yeah, now same thing, what do you mean by maximal irreducible subspace? That means that if you think of the all the irreducible subspace of a I mean of a as a collection, so these are the maximal elements. So there is a result in ATIA in chapter 1 exercise 20, that is proof maximal irreducible subspaces yi are closed and covers so think of the space as X, so covers X. Why? Now okay, this is reference as chapter 1 exercise 20. Okay, ATIA. I should also mention the name of MacDonald because it is his book too. Okay, so one thing is clear that maximal subspaces always have to be closed, because if y is irreducible then its closure are also irreducible. So maximal subspaces always have to be closed. So the first one is fine, and the second one is that any point is closed, at least in our first of topology or T1 topology. Then can think of, okay, think this way is better. I think any single point is irreducible, so it should be contained in a maximal irreducible subspace. Anyway, now if we assume that the intersection of all the yi is non-empty, then any neighborhood of any point of x intersects any neighborhood of small x, where x is a point in x contained in so then one can see that capital X equals to small x closure, right? Because if you take any point from capital X, then any neighborhood of any point intersects neighborhood of small x. So yeah, this is the definition of limit point, and so every point of capital X is contained in the closure of this small this point. So in that case, the statement that is a finite union of irreducible closed subsets. So I already told you that singleton is irreducible and closure of irreducible set is irreducible. So yeah, X is irreducible itself. So it is a finite union of irreducible subsets. Now in the case I capital I mean if this intersection is empty, the set x minus yi is an open cover of x, and this necessarily has a finite subcover since again this is also a result. I cannot prove every one of them, then it would be a topological class. Okay, this X is Noetherian, and so it is quasi-compact. This yields a presentation of X as a finite union of irreducible and closed maximal subspecies. Okay, so what is this actually saying? That if the intersection is 0, then the set that x minus yi is an open cover, right? And this is necessarily has a finite subcover, and so that means what? That this finite subcover, that means x minus yi union x minus yk, say, is x. So from here you can actually see that x equals to y1 to yk. So yeah, so we are done. Now we will come to our main result, that is proof of the theorem. That is, if A is a Noetherian ring, then spec A is a Noetherian topological space. Now what I have said earlier is that if a topological space is Noetherian, then every descending chain of closed subsets has to be finite. That is, the whole collection of closed subsets has to have a minimal element. Now assume that V of a n, where n belongs to n, this A is Gothic and it means the ideal is a decreasing sequence of closed sets in spec A. We assume that n are radical ideals. So we know that there is an 1-1 correspondence between these radical ideals and varieties, these closed subsets. So yeah, since V of A is V of R of A, so since this functor V is an inclusion reversing bijection from the set of all radicals of A to the set of all closed subsets of space K. This chain yields an increasing chain AN, which must stabilize because A is an Noetherian ring. Stabilize by Noetherian condition. Now this implies that the initial chain stabilizes and therefore space K is Noetherian topological space. So this is actually called an affine variety. So you have seen that actually this is a Noetherian topological space, and I also asked a question that if the converse is true. So think of this for 5 minutes and we'll resume. Okay, so let us uh, do this converse not true. So in example, let equals to k of x1 x2 be a polynomial ring over a ring A with infinitely many variables adjoint. Let equals to x1 x2 be the ideal generated by the squares of all the variables. Then A bar so it should be x1 just go like this, yeah, is not Noetherian, right? Because A is not, and if you see the elements we are leaving, that is x1 x2 x3 up to infinite terms, this is telling that this is infinitely generated Noetherian module, infinite generated module, so it is not Noetherian. But if you note at the let's see, if you look at the radical of this ideal, that would be x1 x2 this. Thus spec of this to spec if a radical of this which is maximal ideal, so it is a point. This is maximal ideal in A. So lambda is not a Noetherian ring but spec of is Noetherian. Because this is a point, so you know that in singleton point, so it will have only closed one closed chain that is also of length 1. So yeah, okay. So I hope that you understood the proof, but uh, the the main thing that matters is that the theorem, which is very important. Okay, okay, okay. I'll do some other problems. Okay, uh, let's move on to other problems and start with problem 2. Prove that prove that every PID is Noetherian. PID means principal ideal domain. You already know what that is. And the second part is prove that the ring generated by 1 and root over minus 5 over z is Noetherian. Okay, take 5 minutes for this to try, and we'll meet at 6:75. So yeah, we'll start with problem A. Solution. If A1, A2, A3 is a chain of ideals of the principal ideal domain R, then equals to union of AI is an ideal. Indeed, to see that it is closed under addition, note that if x comma y belongs to A, then x belongs to AI and y belongs to AJ for some I comma j. Now without loss of generality, I less than equals to j, so comma I belongs to AJ, and so x plus y is to AJ of A. Since R is PID belongs to R alpha for some alpha belongs to A, if alpha belongs to AK, then whole A belongs to alpha of K, proving the ascending chain condition. Now the second one is actually an interesting problem. So we'll use the Hilbert basis theorem for the first time in this assignment. Let P be a map from Zx to Z of root minus 5 such that your fx goes to f of root over minus 5. If A1 is contained in A2 is an ascending chain of ideals in z of root minus 5, then P inverse A1 is contained in P inverse A2 is an ascending chain of ideals in z of root minus 5, sorry, z of x. Hence, it must terminate as z is a PID, so z is Noetherian, and yeah, by Hilbert basis theorem, your Zx is also Noetherian. So this ascending chain must terminate. This implies that the later chain, so A1, A2 terminates. Now I will try to do a problem that includes group action. Actually, finding problems that is only based on those theorems are very difficult. So I tried to make this thing little interesting. So first I tried to include this topological space arguments. Now I will try to include a action based a problem based on group action and this Noetherianness. Okay. I think it will be interesting. So let's see. This should be problem 4. Yeah. This should be problem 3. Let A be a Noetherian ring be a finitely generated A algebra G a finite group of A automorphisms of B and BG that I am defining as x belongs to B such that fx is to x for all A belongs to G. So this A bracket x means if acting on x, that means all the elements of B that are fixed by this group action. So the interesting thing is to notice that so that BG is a finitely generated A algebra. So this theorem actually is very useful in a topic called geometric invariant theory in algebraic geometry. So I thought this might be helpful for those of you are hoping or trying to have a career in algebraic geometry. Since BG is closed under multiplication. Yeah, these are the things that you can verify, that is, if f of xy, if you multiply f with xy, then it should be fx of y, and then f of x should be x, then it should be xy, and for addition it is trivial. Since bg is closed under multiplication and addition, it is a subring of b. So we claim that for every b belongs to b, there exists an monic polynomial from bgx such that f of b equals to 0. That is, b is integral over bg. Yeah. So the action of G on B extends in a natural way to an action of G on BT, where G acts trivially on T and acts on the coefficients as the action on B. For each sigma belongs to G, sigma of ft should be to G T minus sigma of lambda B should be equal to lambda of G T minus lambda B, which is f of t. So it follows that all the coefficients of ft are G invariant and so lie in Bg. So B is integral over Bg. So Bg is a sub-algebra over B. Now A is Noetherian, B is finitely generated over A. So claim let A be a Noetherian ring and be a finite type A algebra, then B is Noetherian ring. So let me recolor this thing. Then using this any A sub-algebra is finitely generated, hence Bg is a finitely generated A algebra. So what I did was that showing that B is integral over Bg, that means there exists a polynomial in the ring, in the polynomial ring of Bgx, so that if you put B in that polynomial, it would be 0. So from that would show that Bg is a sub-algebra, that means it is subring and also closed under this multiplication. So yeah, this is a sub-algebra, and now A is Noetherian and B is finally generated over A, so B is Noetherian ring, and so yeah, yeah, any A sub-algebra, that means an ideal, yeah, this should be closed, this should be finally generated. Now proof of claim. but I think this proof was done in your lecture, so I will skip this proof here. Yeah, actually saw the lecture now and saw that it was done there. Okay, we move on to the next problem. So that is problem 4. Suppose 0 A B C G is a short exact sequence of R modules. Prove that if C is a free R module, then there exists an R module homomorphism J of C to be satisfying I B of F of A J of C. That means I'm trying to show is that this pre-module is a projective module, but since projective module has not been introduced, just try to remember this as this property, but this is basically the definition of projective module. Okay, and okay, add another that conclude that B is isomorphic to A plus C. Okay, I will prove this, but since I need a break and also you can try, we'll meet after 5 minutes. So earlier I said something, I was thinking till now that maybe and the so using this and the result that b is integral over bg. You have to use both of these result, then you can say okay. Okay, so let us do the proof of this theorem. I'm sorry I took a long break because I was thinking of what I did earlier. Okay. Let is equals to psi belongs to I be a basis for C. Since it is a free module, since G is small g, look at this theorem. Since small g is surjective, for each I we have bi to be such that g of bi big psi. Set j0 big psi as bi for all I. This gives a set map j0 x to b satisfying h of j0 to ic. Since C is free with basis x, j0 extends to an R module homomorphism J C to B, and the linearity of J together with G of J0 IC gives G of J on C. Now take B of B, small b of capital B, then this is for part 2. Then G of B minus J of G of B equals to G of B equals to G of j of g of b equals to g of b minus g of b 0. So that b minus j of g b is in the kernel of G, which equals the image of F. Thus, b minus j of g of b equals to f of a for some a of capital A, and therefore b equals to f of a plus j of g of b, showing b equals to f of capital A. I'm writing down here j of c. Now suppose f of a1 to j of c is in f of a intersection j of c for some a1 belongs to a and c belongs to c. Then 0 equals to g of f of a1 to g of j of c equals to c. So c equals to 0, and hence j of c equals to 0, showing that f of a intersection j of c equals to 0. Thus b equals to, because intersection is empty and earlier I have shown that they are sum, so this is direction, right? And I had asked to conclude that b is isomorphic to a plus c, a direction c. So for the final statement, f is 1 1, so f of a is actually isomorphic to a, and suppose j of c equals to 0, some c, then c equals to g j c equals to 0, showing j is 1 1. Thus c equals to j of c it follows that B is isomorphic to A plus C. So actually done. Now we'll do an interesting problem, and I think it will be our last problem today. uh, so yeah, should be problem 5. Let A be a finitely generated K algebra. K is a field here. Then show that A is an Artinian ring if and only if A is finite dimensional as a K vector space. Okay, think for this 5 to 10 minutes, then I will start. So we will be doing this proof. Okay, first do the converse thing. Suppose that A is a finite dimensional as a K vector space. Consider a descending chain of submodules A equals to am into, since K belongs to A, each mi is in particular a K vector space. Since A is finite dimensional as a K vector space, mi are finite dimensional K vector spaces. So now it must be that the chain stabilizes, as otherwise we would have an infinite descending chain of finite dimensional K vector spaces. Contradiction. So A is Artinian. Now conversely, since A is Artinian, it has a composition series A m0 m1 mn equals to 0, such that each module mi by m plus I is a simple A module. Simple A modules are isomorphic to some A by M for a maximal ideal M. But A by M is a field that is finitely generated over K, since A is finitely generated over K. Hence by Zariski's lemma. That the lemma itself is A by M is a finite field extension of K, then it is a finite dimensional vector space. Hence over K. But now we see by induction that as a K vector space, A is isomorphic to M0 by M1 direction, M1 by M2 direction, Mn-1 by Mn, which is a finite dimensional K vector space, since each Mi by M plus I is also so we are done. Okay, you have any doubts, you can contact me, and keep attending the classes so that we can discuss, not this one-way classes. It gets boring for me too. Okay, thank you.